Welcome to this short video where we will discuss the instructions and ways in which you should approach the solutions for the activities within the external activities notebook for the Part A lecture notebook of Module 4. The first thing you should do is mount your Google Drive and then check to set the module path for wherever you've put this My Function Classes module that is in the repo on GitHub and also available on Canvas. I'll upload it there for the students that are taking this class at CU Denver. So once you've set that module path to wherever the folder is that you've put this file, you run these code cells and you've imported My Function Classes as myfc and numpy as np, and you have what you need in order to start this first activity. This first activity has you explore a bisection variant called regula falsi, also called the false position method. It's actually quite simple. It follows 3 steps. If you click this link, you will just take yourself to this Wikipedia article. You could scroll right down to this part of the Wikipedia page and kind of look at this picture. It shows you basically what's going on with this method. As opposed to the bisection method that takes a point A where f of A is negative or positive, and a point B where f of B has a different sign than f of A, and then taking the midpoint, that's what the bisection algorithm does. This false position method says, well, maybe we could do better. We could actually use the function values themselves to construct a line that's approximating the function between those values because it's based on the function values at these 2 points. And then the root of that line is potentially a better approximation of the root of the function because the root of that line is actually based on the actual function values because the function values were used to make the line. That's it. That's the whole concept. And then you just keep repeating, just like you do with the bisection algorithm, except instead of dividing intervals in half, you're just picking the new left or right endpoint based on where the root of this previous of the line was. That's the only difference. And this is the whole thing. They've done it for you. If you look at this equation right here, this is all that changes. Instead of this C at the kth iteration being the midpoint of A and B, you just have to compute this. That's the only line of code you have to change in actually the way in which you compute the root. That's it. If you just go to the algorithm inside of the bisection algorithm and say where was C computed as a midpoint, and you change it to that formula where you take B minus f of B times B minus A over f of B minus f of A, or you use this other form, just pick one, A times f of B minus B times f of A divided by f of B minus f of A, where A and B are whatever the current interval values are in the code. That's all you're going to do for C. Instead of it being A plus B divided by 2, the midpoint, you're just going to replace it with this formula. If you replace nothing else, everything else will work. That's all you need to do. That's all I'm asking you to do here. So in this activity, well, I'm asking you to do maybe a little bit more. I want you to do the following things. So I want you to first look back at activity 1 in the Part A lecture notebook, and what I want you to do is follow these 3 steps below to subclass from the MyFunctions rule class, which was imported from the MyFunctions class module, so that this subclass has a compute false position method attribute. That's what I want you to do. Step 1. I want you to look at what is currently in this MyFunctions ain't false subclass. All right? So if you look at this, I'm creating a class, MyFunctions ain't false, because I'm going to use this false position. I'm subclassing it from the MyFunctions rule class, which is in the MyFunctions, this module that I've imported, that I'm giving to you to import, that was based on this part right here. So I initialize it, and I'm just calling the superclass, the parent class, and initializing it. And the one thing was that method had I believe a method for setting the bisection parameters. Now again, the false position is just like the bisection in every way except for how that C value is computed. It has all the same types of parameters. So what I want to do is have a method that's called set the false position parameters, but it should just call the set bisection parameters because they all are just the same. They do the same thing. The only thing that I need to do really is compute this false position. This is what you need to do. So that leads us to step 2. Complete the method. Compute the false position. So make sure that this new compute false position method attribute, test that the conditions are appropriate for running this algorithm. Here's a hint. All of this can be done with a copy, paste, and edit of a single line of code. Again, yes, really. The false position algorithm differs from the bisection algorithm minimally. If you simply copy and paste the compute bisection method from the myFunctionsEnhanced, which is a grandparent to the myFunctionsRule class, into this method, then you only need to edit a single line of code in that method involved with computing C. That's it. So go to this myFunctionsEnhanced, where the whole compute bisection method was originally defined. You can go look in the Lecture A notebook. You can look inside of this Python module. Whatever you want to do, just get it, copy and paste the contents of the compute bisection method into here. That's what I'm asking you to do. And then change that single line of code where C is computed as a midpoint so that it uses this formula. That's it. Almost. Step 3. All the code comments that I had put into the compute bisection refer to the bisection algorithm. So those code comments need to be updated. Make sure any code comments that are in here should be referring to the false position method, not the bisection algorithm. So that's it. Just update the code comments, because when you copy and paste, you're going to copy and paste code comments in that are wrong because they're referring to the wrong method now. They need to be referring to this new method, this false position. So if you do that, you will have this done. And then what I'm asking you to do is just run these code cells, and I'm leaving these plots in for you in this video. I will clear all this output, but in this video I'm showing you things should work correctly. This plot should be made. Once you run everything, you should see a plot that looks like this. If you run this, and you say, what I'm comparing is the bisection, right? Because these fantastic functions, this function right here that I'm creating from my functions ain't false class, it's subclassed. So it has the compute bisection method and the compute false position method, which means I get to compare them. I can have all the same parameters. So when I set the false position parameters, remember, it uses the same parameters as the bisection algorithm. So they will use the same parameters, but the root's computed differently. It's computed based on the line instead of the bisection of the interval. And so I can compare these. And you can say, oh, if I had like 2 iterations of either of these methods, and I looked at the bisection algorithm, and then I looked at the false position algorithm, look at what happens when I start with -1 and 2, and then I'm looking at the approximate root. And you can see, oh, the bisection algorithm looks a little better than the approximate root after 2 iterations of this method, based on my first initial guesses of -1, 2, and -1, 2. Or excuse me, those are the intervals for the plotting. What am I saying? -1 and 1.75 are my initial guesses for the root, or for the interval that contains the root. But look what happens when I go to 5 iterations. When I go to 5 iterations, here's what the bisection algorithm gives me as an approximation of the root. It's not bad. It's getting close. It's 1.49. But look at the false position. It has now done better. So that leads us, so you should be able to run those and get those types of results. That leads us to this last set of instructions that end activity 1. In computational data science, we often must choose between implementing competing algorithms that solve the same class of problem, but in different ways. An important lesson here is that if 2 or more algorithms exist to solve a problem, then there will be cases where one is preferable to the other. The question then becomes, which should you apply for a particular problem? I'm asking you to use a mixture of markdown and code cells below to compare the bisection algorithm and false position method, more so than what I've just done. So I've already done some comparisons. Make your own. You may find, again, the wiki articles useful to reference here, as well as doing some of your own Google search. In fact, there's lots of good information in this about what's going on. So if you scroll down in this Wikipedia article, there's like these practical considerations, and then there was, let me actually even see something else. Numerical analysis, history. There was a few good things I saw while I was reading here, where they gave some idea about, bisection algorithm gives you a guaranteed rate of convergence. False position often works better, but not always. What I want you to do is just read a little bit about this, and then I want you to describe and implement problems where just one method seemingly does better than the other. For example, what if the function is approximately linear near its root? What happens if the function is very flat near its root? Here are things to consider. Can you explain why that is happening, basically why one is performing better than the other. So in each of these code cells, you should just do something kind of like what I'm doing up here, where you actually get one of these to show that it's clearly a better approximation to the root than the other. So like these are both terrible approximations at this point, but here you kind of see, oh yeah, at the same iterations with the same setups, false position did better than the bisection here. Why? Why do you think that is? I'm kind of prompting you to think about some of the reasons why that could occur, and again, you can read about it a little bit. And so this is what I want you to do, is do those examples and just explain what you found, what you read, your interpretation of the advantages or disadvantages of these two methods, to just compare them. Just lay out the pros and cons, and that's it. You do that, you're finishing this first activity. Thanks for listening, and then the next part of this video we'll discuss activity 2. The second activity deals with Monte Carlo integration. The basic idea is to estimate the integral of a function over a set A using the average of a random sample of function values. The question is this: how do we generate a random sample of these function values in order to do this? Well, it's quite simple actually. We generate a random sample of x values in the set A, we evaluate the function f at these random inputs, then we simply compute the sample average of A. Are there any sticky points to this? Well, a few simple examples will illustrate just about all you possibly need to know in order to understand how to do Monte Carlo integration correctly. Suppose that the function f of x is equal to 5 on 0, 1, meaning it's constant on the interval 0 to 1. We saw an example about a constant velocity in integrating to get displacement in the lecture, so we actually know that the integral of the function 5 over the interval 0, 1 is simply 5 times the length of the interval. So it's 5 times 1 gives 5. Well, this is what our MC estimate, our Monte Carlo estimate, should be approximating. Well, guess what? Any random sample of x values between 0 and 1 will always give corresponding function values that are 5 because f is constant on this interval. It's always equal to 5. So what would the sample average be of these randomly sampled function values that are all 5? Well, 5. Whoa, the MC estimate is exact in this case. Isn't that amazing? It doesn't always work out that well. In fact, what if the function was 5 but on the interval 0 to 2? So all we have done is change the set from 0, 1 to 0, 2. So we made the interval twice as long. We know the exact answer to the integral of the function that is 5 over the interval 0 to 2 is 5 times 2 minus 0 is 10. However, by the same reasoning above, any random sample of function values will produce a sample average of 5, not 10. So what if the function f is 5 on the interval 0 to 0.5? Again, the exact answer is 2.5. Yet again, any sample average of function values will produce 5, not 2.5. So what is going on? How do we fix this so Monte Carlo integration is actually going to work? Well, what we need to do is actually weight the sample average of the function values by the size of the set A. So in summary, if x sub I is a set of n values that are a subset of A, is a uniform random sample from the set A, and we let mu of A denote the measure or size of A, then a Monte Carlo estimate of the integral is simply given as mu of A times that sample average of function values. So the length of the interval being 0.5 here, and this example, this last example, or the second to last example being length 2, that's all we had to do to get the value right, is we just had to multiply by the size of that interval. So that's it. That's the only thing. So we play with this below and we'll discuss what we're seeing. But first, just take a pause. You might want to reread that just to make sure it all made sense, and then we'll continue. So in this function, we are computing the Monte Carlo approximation on a one-dimensional space. So it takes f, a, b, and n as the parameters of this function. Now what we're doing is a and b are the interval, the left and right endpoint of an interval we want to integrate on. N is going to be the number of random points that we want to take in that interval. So we want them to be uniform. We're sampling from the random subpackage. We're using the uniform random sample method within the random subpackage of NumPy. NumPy was imported as NP above activity 1. And we're creating our random set of x values. We know the measure of an interval is just defined as the right endpoint minus the left endpoint. That gives you the length, the size of the set. We then use the mean function of NumPy to compute the average, the sample average of the function value. So we evaluate the function at all these x random points. We take the mean value. That's the average function value. So our Monte Carlo estimate is now just mu a times this average function value. And we are returning the average function value as well as the Monte Carlo estimate as a tuple. That's what that function is doing. It's not complicated, but it's worth seeing. It's just we're working with a few different kind of built-in methods within NumPy. So now let's do some numerical experiments and analysis. Below, we show how to do three things. We use this compute 1D MC approx function defined above, and we understand the variability in the estimates we're typically going to get due to random sampling, because mostly we're going to be looking at estimating intervals of functions that aren't constant. We're going to analyze the rate of convergence, because you might recall we looked at the rate of convergence for these rectangle rules in the lecture notebook, but we have to understand rate of convergence in a different sense here because we have randomness in our answer. So what do we mean by rate of convergence? Here, it's a little bit more subtle. And we're also going to create some interactive visualizations of this function that help us tell a story. So I'm going to create this function, that is this lambda function, that's just x plus 1 times x minus 5 times sine of 3x. And now I'm going to look at three different Monte Carlo approximations. Now, if you look at this code on lines 2, 4, and 6, notice there's no difference between any of these lines of code. Not a single difference. They're all exactly the same. But when I run this, as I'm about to, you see I get three different answers. What is going on? Well, I generate random samples in here, and then I'm creating random function values and taking the average. So there's variability in the answer. And it just so happens with this function that has quite a bit of oscillations and interesting behavior that 100 points is just not enough in order for my estimates, the variability in my estimates, to be small enough for me to reliably use any of these estimates as a good value of a good estimate of the interval. So this is just about variability. What happens if we use, let's say, 1,000 trials, though? So I'm going to use 100 estimates. So I'm still going to use I'm going to basically create crappy estimates of the interval. I mean, you can see these things are all over the place. Negative 0.87, negative 1.39, negative 2.47. They're all quite off from each other. You're going to see different values as you run this because where the random seed is going to be different. We're not setting a random seed here. But you see there's quite a bit of variability in these values. So imagine that I compute 1,000 estimates. I'm going to create an array of zeros to hold all of my approximations, and for each of my, basically each trial of my 1,000 trials, I'm going to compute a Monte Carlo estimate with 100 samples of the same integral, and I'm going to store that in this array. So for I in range 1,000, I'm going to create the ith index of this array. I'm going to store in it, I'm going to assign that value what this interval approximation is. So remember, the MC estimate is the second output, and that's why I have 1 at the end here. So I use the average function value for some of the illustrations. So I'm going to do that. I'm also going to import all these things that are useful for visualizations. And now here's what I'm going to do. I'm going to make a figure. It's already kind of generated from a previous run, but I'm going to do it. I'm just going to go ahead and do it again. And in that figure, I'm going to create a histogram. And in that histogram, I'm going to show this 1,000 interval approximations. And I'm going to actually put a vertical line in black. That's the black line. I'm using the quad function to compute a rather accurate approximation of the integral. So look at this distribution. It looks like something that looks kind of like a normal Gaussian shape distribution, kind of like a bell-shaped curve. It has that structure to it. And if you look at where this mode is, where basically the approximate mean of that distribution is, of this sample of estimates, the Monte Carlo estimates, it seems to agree with the actual integral based on this quad value. This is this quadrature function that creates really accurate estimates. So it seems, again, like the mean sample average, which is what I'll do here. I'll just compute this based on my estimates. My approximate mean based on 1,000 estimates is negative 1.65. The actual interval was negative 1.72. So what is this telling us? While any single Monte Carlo estimate might be bad, the expected value, in other words, the mean of all my Monte Carlo estimates, is actually quite good. I mean, it's not too far off from negative 1.72. It's within about 0.07 of that value. That's not too far off. So the MC estimate, the method produces what is known as an unbiased estimator of the interval, meaning that its expected value is exactly the interval we want. Now, we compute a finite expected value, a sample average, instead of the actual expected value of what the distribution is. We're estimating the distribution and then computing the expected value. So there's some error. That's why this is not exact. But if I was to compute instead of 1,000, if I was to do 10,000, and it takes just a slight second to run, and I run this again, you look at that. Oh, that distribution looks far more centered there. And now when I compute this, negative 1.72, negative 1.72. I mean, there's always going to be some digits that aren't matching up because I'm using still finite samples, but my average value, my sample average, is going to get much, much better if I use 10,000 as opposed to 1,000. I just did it so that it ran a little faster. That's why I used 1,000. But then that means that my estimate of the mean is just off a little bit. And you see, I'm getting different values each time because of the randomness. So one of the issues you might say is, well, okay, the expected value is great. The problem is the variance in this estimator, which is describing how much any single Monte Carlo estimate may vary around the estimate you want, meaning the mean value, can be quite large if you use a small sample size. How do you reduce the variance? Increase the number of points used to estimate the average value of the function. So we show this below. So here what I'm doing is I'm using 1,000 trials again, and then I'm creating n's in a log space. So I'm going to go from 10 to the second, 100, to 10 to the third, to 10 to the fourth. So 100, 1,000, and 10,000 samples. And I'm going to do 1,000 trials for each one. I'm going to create interval approximations as a 2D array that has 3 rows and number of trials that are, so 1,000 columns. And then for each of my n values, so n of I, so basically for 100, for I basically being the 0, it'd be the first one, so I'll grab the first n's, so it'll be 100. I'm going to loop through 1,000 trials, and I'm going to store this in the array for each of those trials. So I is 0, and I just have this nested loop. When I then is 1, so it's the second iteration through that outer for loop, the inner for loop iterates again, except this time it's using n's of 1, so it's going to use 1,000, and then the last iteration it will use 10,000. So first row of this array will contain all my approximations with 100 samples, all my 1,000 approximations that I'm doing. Then I'm going to have 1,000 approximations with 1,000 random samples in the Monte Carlo estimate in the second row, and then I'm going to have 1,000 estimates with 10,000 samples from my Monte Carlo estimates in my third row. That's what this is what this code cell does. Now all I'm doing here is I'm looping through and nesting these histograms on top of each other. I'm just plotting them on top of each other, and I'm controlling how transparent they are as a function of the iteration number. That's all I'm doing. Then I'm creating a label that's saying how many values n were used in each of the Monte Carlo estimates. So you can see when I use 100 samples, I have this wide distribution. When I use 1,000 samples, the distribution becomes remarkably slimmer, you could say, kind of tighter around the mean value than the one in blue with 100. And when you use 10,000 samples, it's even more concentrated around that mean value. That's all that's happening. So in the histograms above, again, we see that increasing n, the number of samples used to estimate to create a Monte Carlo estimate, reduces the variance in the Monte Carlo estimate. Each estimate will be more accurate it will probably be more accurate because it's more likely to be near the mean. So that's all we're seeing. So if you want a more accurate Monte Carlo estimate, just make n larger. And you expect that any individual estimate will be a better representer of the mean because the estimates that you're getting are more concentrated around the mean. That's it. That's all that's happening. Now, if you want to understand how this converges, what you're really trying to say is, how is the variance decreasing, or the standard deviation? So this code cell right here is creating a plot of a figure on a log-log plot of my n's values, and I'm computing the standard deviation of my approximations. I'm doing it around axis 1, so I'm going across the columns. And you can see, as I went from 100 to 1,000 to 10,000 samples, there's this steady decrease in terms of the standard deviation of my Monte Carlo estimates. And you actually see by increasing 2 orders of magnitude, my standard deviation appeared to decrease by an order 1. And you can actually see this as well when you can use this polyfit. This is just kind of like what I was doing in the lecture notebook, except I'm using this standard deviation instead of the errors. Because the errors in some sense aren't really relevant here, because the Monte Carlo, the average value of all of these Monte Carlo estimates, the true average value, not my approximation of it, is the actual integral. So the expected error that I get is 0. The actual error I'm going to get is based on the standard deviation. Like, how variable are my estimates? And you see that you have a negative 0.5, meaning that you have to go 2 orders of magnitude up in the number of random samples in order to decrease the standard deviation by 1 order of magnitude, because it has a slope of negative 0.5 in this log-log plot. So that value of negative 0.5, by the way, is actually a theoretical rate guaranteed by the central limit theorem. You should really take some probability theory and statistics classes, is the lesson here if you haven't already. What this means is that for each order of magnitude increase in the number of samples, the standard deviation is decreased by half an order of magnitude. Just repeating myself, but it bears repeating. That is something that you get from the central limit theorem, and it's used in a lot of statistical in probability classes when discussing p-values, when estimating average values. When you look at confidence intervals and average values and understanding what a p-value is for a hypothesis test, there's a central limit theorem lurking behind that. The fact that you could have used a p-value at all, it's based on a normal distribution, and trust me, this is all back there somewhere. Anyways, is this worse than the left, right, or midpoint rules for the deterministic methods? Yes, I would say yes it is, except there's a huge caveat here. The geometric methods for approximating integrals only work in extremely low dimensions. Geometric or other deterministic quadrature, cubature, they go by many names, methods for approximating integrals suffer from what is known as the curse of dimensionality. You could look this up. We will not dwell on this here, other than to say that as the dimension goes way up, the quality of the deterministic estimate often goes way down unless an exponentially increasing number of points are used to estimate the integral. However, the rate of convergence of the Monte Carlo estimate is independent of dimension. Although this does not quite tell the whole story, it is a big reason why random or pseudo-random approaches to estimating integrals are preferred in high dimensions. And in a lot of data science applications and computational science applications, it's not unusual to compute integrals over spaces that can even be approximately, well, nominally infinite dimensional, but usually truncate, and they can be, of dimension 20, 100, 1,000, a million. There's no way you're going to use some sort of deterministic method. You have to use Monte Carlo, quasi-Monte Carlo type methods to work there. So with that being said, the rest of what we're getting at, we're almost to what you need to do. I have this function for plotting the Monte Carlo estimates. I'm just computing everything right here, this one line of code, and everything else below is for plotting. The only difference really between this and the type of visualization I was showing with rectangular methods is I'm creating a rectangle based on the average function value height. That's kind of it. So all this code was borrowed from how I was visualizing like the rectangular methods, except I only have one rectangle, the average rectangle. And so then this allows you, if you run this code cell, to kind of play with this function we were looking at, this lambda function, with that plot MC1D function I just made. So I'll just show to run interact. You can just see what's going on. The area under the curve is shown in that shaded gray area, and my Monte Carlo estimate produces an estimate of the integral, and it's just based on this average rectangle. Now, if you run interact, if you don't change anything but run interact over and over again, you'll notice that average rectangle shown in kind of in purple color here is changing. Why is that? Again, it's a random estimate. It changes over and over again, and it's very visual, like how much it changes. But if I make n, say, I don't know, I just move the cursor up, 21,380, and I run interact. Okay, there's my estimate, 3.81. There's my, rectangle. If I run it again, you're seeing a slight variation in these function values, but you don't see a big change in that. I mean, they're not big, and the rectangle's not changing much. The variance in these estimates has decreased when I have 21,380, and I've made it so you can go way up. So this is 100,000 samples. Right there, 3.85, I run this again. 3.84, I run it again. 3.87. So I'm only changing this decimal place right here, and it hardly changes you see this, the rectangle is not changing to the naked eye. But if I go way down to like 10 samples, my estimates are going to jump all over the place because there's a lot of variance in them. So this is just something for you to play with, just to get more intuition about Monte Carlo sampling. Okay, your to-dos. Finally, right? You've been listening to me talk for like 16 minutes on this part of the video. Feel free to create many new code and markdown cells below as you work through this activity. What I want you to do is complete this wrapper function, multiple 1D MC underscore procs. There were underscores everywhere there, I just didn't pronounce them. In the code cell below, except that we now assume n, what it's getting here for n, is a list of integers containing the different numbers of random points used to approximate the integral. The wrapper function also has an additional parameter, numTrials, which is an int type that specifies the number of times the number of trials to repeat the approximations for each value in the list of n. Values. The default numTrials is set to 10. Basically what I'm doing here is trying to functionalize what I did in the code up here. It's basically trying to do this, except allowing you to change some of the information here and pass something like n's as n instead of n's. But otherwise it's very similar to this code cell. That's what I'm trying to accomplish in this function. So what's going on here? This function should output a two-dimensional array of shape length n and number of trials. So each row is associated with the n array, and then each column is associated with a particular trial using that n value from that array of number of points used in the estimate. So the ij component gives the j plus 1th MC approximation of the integral using the ith ni random points from that list. Again, you have to complete two things. Complete this part, and look at that previous code cell I was just showing you as for inspiration. And I've kind of already told you in these instructions what needs to go in here, and what should be here is very similar to what I wrote before. And then all I want you to do is, after you run that, is take a number of different lambda functions of your choosing. A number, two, at least two. And including these ones, right? So x and x squared. So in at least one of your choosing. Okay, so three functions. These two that I gave you, x and x squared, code them up, and at least one of your choosing. Compute the errors of the MC approximations of the integrals. And then use n, you can just copy and paste this in, have a be 0, b be 1, and then for each function create an array of shape, length, and number of trials to store the errors. So what I want you to do is you're going to compute these integral approximations. Use the quad function to actually compute an accurate approximation of the integral for each of these functions. Use for each of those functions, then you have this associated array of integral approximations. Create an array of errors. That's it. I want you to create an array of errors. That will complete this part. So you could have if you have three functions, you'll have like errors 1, errors 2, and errors 3 associated with the function x, x squared, and whatever function you choose. You are then going to have these arrays of errors. You will complete this part. And then for each of those different functions, I want you to create two separate log-log plots. All right, two separate log-log plots. And that's for each of your different lambda functions, which means what? You need 6 log-log plots if you have 3 of these functions. I want you to have a legend that shows the means and the variance over the number of trials of the computed errors versus the number of random points used in the MC approximations. So I didn't show you the means. For the means plot, you should compute the absolute value of the mean errors, not the mean of the absolute value. So compute the absolute values of the mean error. So take the expected error, right? Use the mean of the errors, and then take the absolute value of it for each of these sample sizes. All I want you to do, just so it's clear, I basically want you to produce this plot. But I also want you to produce it, I want you to produce it for each function, but I also want you to produce a plot where instead of this, instead of the standard deviation of the errors, and it's based on the errors array now instead of in a prox. I also want you to do one where you use the mean and you take the absolute value of the mean. And you need to take the absolute value of that mean because it's a log-log plot. It needs to be positive. So that's it. That's all I want here. I know it looks like I'm asking for a lot. I don't want that much. What I want you to then do, though, is comment on your results. Kind of explain, try to interpret what's going on, because some of these might seem a little strange, and I want you to think about them a little bit. And if it's strange, I think the ones that might seem strange are the mean errors, and I think that the reason they might seem strange is because, again, the estimate's unbiased. So that could present some interesting things here. That's it. I want you to comment on that, and you will complete this second activity.